So these are my collaborators. And then the CubeSat is an idea how to make new dust measurements around the moon. I imagine you are all familiar with that the Earth is receiving about 40 to 50 tons of cosmic dust, cosmic material every day. If you scale that to the moon, that's about 1 to 2 tons a day that is hitting the lunar surface. LUDI was a mission about 10 years ago, Lunar Atmosphere and Dust Environment Explorer. That was some of the measurements were dedicated to see what happens when you are bombarding the surface of the moon and generating secondary ejecta particles. LUDI was confined to the near equatorial regions of the moon. And one of the instruments was the lunar dust experiment. On the top right is the height versus time through the mission. The top left is how this instrument is working. When a dust particle comes in and hits the surface, it generates a plume. We are flying through that ejecta cloud. Every little impact generates a pulse that I can tell you the size and even the speed of the particle. This is all the data we collected in about 100 days or so. Time versus the impact rate. This little 10 by 10 centimeter squared instrument was hit on the order of once per minute flying around the moon. And of course, there was these special periods when, on the ground you are enjoying shooting stars. LDEX detected the enhanced dust cloud in the periods of meteoroid streams. Based on these measurements, we have a model how the ejecta cloud is engulfing the moon with typical densities of, maybe 3, 4, 5 times 10 to minus 3 per cubic meters. That's on the left is all the data we collected. The instrument cannot look into the sun, so there is a section of that missing that we can then analytically expand. That's the dust cloud around the moon. So imagine that there is an impact that generates a puff of plasma, puff of dust, and then the instrument is, the spacecraft is flying through, and then you have this characteristic double lobe of the enhanced impact rates. We had several of those as through the mission, and there's a couple examples. This is real data. I just collecting them and normalize them. And the ones at the bottom, of course, you have a very short duration flying through. The ones towards at higher altitudes, because of the expansion of the plume, it will take a little longer to fly across. Nevertheless, you could use these to figure out where the impact happened, where the excavation happened, where the dust particles that we are detecting coming from the surface. That's the very idea of the SUDA instrument that is part of the Eclipse mission going to Europa. And as you're generating ejecta clouds, and we are lucky because we had the Galileo mission, which told us how much dust is engulfing these various icy moons at Jupiter. So as the various trajectories would fly over the surface, you could trace back the particles, and that instrument I will show in a second will tell you the composition, some cases even the isotopic composition of every single particle that hits the instrument. That is in fact a small sample from the surface. Altogether, then you will generate a surface map, what's making up the surface of Europa. A similar question is important to us in this community. What is actually the content of permanently shadowed regions? So imagine that you would fly a LUDI-type mission on a polar orbit. As you fly through the permanently shadowed regions, they are permanently shadowed regions from the solar wind or solar radiation. You cannot shadow or save them from dust particle impacts. They will come at all times, at all places, will generate ejecta, and as you fly through, you could look into the content and tell me what's inside a permanently shadowed region. So this is imagine an LRO type orbit. We can then figure out then in a month or so how much real estate you would map on the northern hemisphere, on the southern hemisphere. based on our understanding from ground-based measurements, would be the southern toroidal source and the northern toroidal source hitting the surface, where it hits the surface, how much dust it will generate, how many what is the impact rate that is pointed here, if you were fly an LDEX type instrument. Of course, there too, we have some concern. It's difficult to map the entire surface because our instrument cannot ever look into the sun that would saturate our signals. So here is LODI, LDEX, the lunar dust experiments that has flown. This guy is peacefully resting on the lunar surface. That was crashed about 10 years ago, April. And on the back is the engineering model. The only difference between the engineering model and the flight model is that the engineering model, the electronics boards are not flight qualified for a classified NASA mission. But maybe a company could take it, or a CubeSat can take it, where the requirements for to be flight qualified are very different. The instrument is good to go. The instrument has been purged for the last 10 years, so it's as good a shape as it can be. And in principle, it can be bolted on to a spacecraft. Getting a spacecraft mission into polar orbit, it's maybe more challenging than getting a little CubeSat on a lunar orbit. So this is a 6U version of a spacecraft where the electronics box is divorced from the sensor, and it happily fits into a CubeSat of 6U. What's important, there is also a little bit of room for aviation and comm, so the spacecraft can go and then hopefully flies through these regions and will tell you the content of permanently shadowed regions. It's not competing with Viper. I hope Viper will go and make its measurement, but it will certainly give you a different way, a complementary way to make a global map of what's in permanently shadowed regions. So imagine
3 minutes. 3 minutes.
Imagine that you have flown this little CubeSat. You have an understanding about the impact rates. Now you could properly size a more complex instrument like SUDA that would tell you the composition. So SUDA, for example, I'm showing at the bottom is a Cassini spectrum of pure ice particles in Saturn's E-ring. Ice is easy to recognize because it will break into clusters, water clusters, and it is clearly showing up in our time of flight mass spectrum. These instruments work with an impact. Sorry, go back one. Anyhow, the one was an ice spectrum. This is a hydrated mineral spectrum, and I will ask you to visit this poster tomorrow. The instruments will take a dust impacts, which generates a puff of plasma. Electrons and ions are separated, electrons collected on the target. Ions are forced into an optic region, initial identical energies. So large, heavy ions arrive later, very light ones arrive earlier, and then you could turn that time of flight mass spectrum into a compositional spectrum. And this little olivine type particle, which is a mineral that has some water content, the water shows up even at 1.6, 1.7 kilometer per sec, which will be your typical speed orbiting the lunar surface. And here I am as a summary. I think it would be a good idea to have this type of a CubeSat and use it as a precursor mission to gauge the ejecta production so you could properly scale and figure out what sort of a more complicated instrument you should fly the next time around. And the SUDA type or an LDEX Plus instrument that would now measure the composition could map from orbit what's in the permanently shadowed regions. Thank you.